This video is going to show you how to work with problems dealing with the ideal gas law. The ideal gas law is a little bit different than the basic gas laws that we've covered in our other videos because the ideal gas law actually involves the number of moles of gas. Also, something that makes it different, and this is a big clue for students when they're trying to determine what type of equation to use to solve the problem, is that you only have one pressure, one volume, and one temperature involved. So those are just some little things to look out for, and they are big clues to tell you, hey, you need to use the ideal gas law. So let's start by talking about the formula. The ideal gas law is PV equals nRT. And I've got a little chart here for you that I think you'll find very helpful. It explains what each of the variables represent. So we're going to start with P, which we already know is pressure. And pressure is typically measured in atmospheres, kilopascals, torr, or millimeter mercury. These are what most beginning chemistry students are going to see. There are other units of pressure, but you're not going to need to worry about those. V is volume, and volume must be measured in liters. Now that also makes this law just a little bit different from the basic gas laws, and by basic gas laws I am referring to Boyle's, Charles, Gay-Lussac, and combined gas law. For those gas laws, it didn't matter what the volume was in as long as you kept it consistent throughout the problem. For the ideal gas law, the volume must be in liters when you plug it in. So if they give you a volume that is not in liters, convert it to liters, and then plug in. T is temperature, and just like in the basic gas laws, it must be in Kelvin when we plug it in. If your temperature is not in Kelvin, it's usually going to be in Celsius. If it's in Celsius, you just add 273 to that number to convert it to Kelvin. Now, N is new for us as far as working with gases, and that is the number of moles. If they give you grams, you simply convert it to moles before you plug it in. So this will have to be in moles when you plug it into your equation. And now we have something that is new for most of you, and that is R, the universal gas constant. Now, if you are a high school chemistry student, maybe even a beginning college student, you probably have a reference table packet. And this reference table packet actually gives you the R value so you don't have to memorize it. If you are a more advanced chemistry student, you probably have to commit this to memory. Now what you can see here is for R, we have three different numbers to choose from. But what I want to point out is, aside from the numbers being different, the only difference in these units is pressure. You can see that volume is in liters for all of the R values. The amount is in moles for all of them, and temperature is in Kelvin. But we have some choices when it comes to pressure. So you simply choose the correct R value for your problem based on the units of pressure that you're working with. So if you're working with a problem that either gives you pressure in atmospheres or perhaps asks you for pressure in atmospheres, you would use 0.0821 liters atmosphere mole Kelvin. If they give you kilopascals in the problem, you're going to use this one. And you're going to want to use the unit of pressure in your R value that you're using in your problem so things cancel out or so you can solve for what they are asking for. This is also a great reminder to you that your volume always has to be in liters, your amount always has to be in moles, and your temperature always has to be in Kelvin. So again, your units cancel out. And once you see the work, that just makes perfect sense. It's very easy. So the R value is a constant. That is typically something, if you don't know it, you can look it up, unless maybe you're taking a test and your teacher has asked you to memorize it. So once again, PV equals nRT, some major differences between this and the basic gas laws. You only have one pressure, one volume, and one temperature in this one. In the basic gas laws, you have two, because remember you have V1, V2, P1, P2. You only have one here. This is also the only law that involves the number of moles and the only law that uses the universal gas constant. The universal gas constant can always be looked up if perhaps you don't know it. Now, a few more things I want to point out that are important when we're dealing with gases. Sometimes you'll see this little abbreviation or acronym, STP. That stands for Standard Temperature and Pressure. And for a gas sample, standard temperature is either going to be 0 Celsius or 273 K. These numbers are equivalent to each other, just different units. Pressures that we're going to see might be 1 atmosphere, which is the same thing as 101.3 kilopascals, which is the same as 760 torr, which is the same as 760 millimeters mercury. These are all the same value, just different units. And last but not least, if you haven't seen this, now's a good time to look at it. At standard temperature and pressure, 1 mole of any gas occupies a volume of 22.4 liters. That's going to be important when you do gas stoichiometry. We're not going there today, but also something to keep in mind. But if you ever get a problem that says at STP, they're referring to one of these temperatures and one of these pressures. And depending on the temperature and pressures that are in the problem, in other parts of the problem, you'll know what to use. So we're going to do 3 examples of the ideal gas law today. It's super easy to work with. I think it's even easier than the basics because you don't have to decide what's your V1 and V2, P1 and P2. There's only going to be one of each. So once you've taken notes on this, after you've paused the video, I definitely write these things down. Let's go ahead and get started with example number 1. So take a second, pause the video, write this down, and now we're going to go through it together. If the pressure exerted by a gas at 25 degrees Celsius in a 0.44 liter container is 102 kilopascals, what is the number of moles present? So what I like to do here is just go through and label everything before we even start. They're asking me to solve for moles, and I know that moles is N. They gave me temperature. Now, I do know that I cannot use Celsius, so I'm going to add 25 to 273, and that is going to give me 298 Kelvin. That's the temperature that I want to plug in. 0.44 liters is the volume, and 102 kilopascals is the pressure. So now that I've got everything labeled, I know that I'm using the ideal gas law. I've got 2 big clues here. I've only got 1 temperature, 1 pressure, and 1 volume, and I also see that they are involving the number of moles. And if they're involving number of moles, ideal gas law is the only thing I can use. So the ideal gas law is PV equals nRT. Now, in this case, they are asking me to solve for N, which is the number of moles, so I've got to get N all by itself. I just divide both sides by RT. This is just basic algebra. You're just rearranging. The RT's cancel, so I'm going to flip it around. N equals PV over RT. This is the equation that I'm plugging into. This is also a really easy equation to rearrange, so I think that makes your life a lot easier. Now, here's the cool thing. We've got it rearranged. We've labeled everything, so all we've got to do is take these numbers, pull them down, and just plop them right where they go. So N equals pressure, which is 102 kilopascals, times volume, which was 0.44 liters, and volume is supposed to be in liters, so I'm okay there, divided by, now I've got R here, and remember R is a constant, that is the universal gas constant, so I've got to take a look at my packet and see which R value I want to choose from. Remember, you've got 3, and you base it on the units of pressure that are being used in the problem. This problem is using pressure in kilopascals. So all I'm going to do is peruse through these choices, and I'm going to find the one with kilopascals in it. It's this one right here. 8.314 liter kilopascals moles Kelvin. So I'm going to plug that in. 8.314 liter kilopascals. I tell my students just cram those units in there. Mole Kelvin. So there's the R value. The temperature was 298 K. And now I've got everything plugged in. So let's make sure things cancel. So I can see the kilopascals will cancel. The liters will cancel. The kelvins will cancel. And that leaves me with one unit not canceling, and that would be moles. That is good news because moles are what I am solving for in this problem. So all I'm going to do now is I'm going to multiply 102 by 0.44. That number will go on top. Then I'm going to multiply 8.314 by 298. That number is going to go on the bottom. And if you need to do that little intermediate step, please do. Some people just put everything in their calculator at once because they're really good with the parentheses. If you're not, or you're not comfortable with it, just do the top and bottom and divide them. So once you divide, you're going to get 0.018 moles. Now, they didn't tell us what the gas was. If they would have, I would have put it down, but they just said a gas, so we're okay leaving our answer like this in this case. And there's your answer. So one note that I would probably make on this example so that you have it for future reference is this number right here, the R value, came from the reference table packet. And it's based on the units of pressure. Which in this case was kilopascals. That's just a good little note to have. So if you are using this later in college, a year or two down the road, you can remember where you got that number. All right, so now let's take a look at example number 2. So go ahead and take a moment, pause your video, write this question down. You might even want to go ahead and try it. Most kids after one example are pretty comfortable with this, but I'm going to do it with you just in case. So number 2 says, what is the pressure in atmospheres? So we are solving for pressure. I'm going to highlight atmospheres too because that's important. Of 25 grams of carbon dioxide in a 4-liter container at 200 Kelvin. So they gave me volume. They gave me temperature. Now, they gave me grams. I cannot plug grams into this equation, but I can plug in moles. So real quickly, I'm going to convert that 25 grams of carbon dioxide, this is just my scratch work, to moles. And we know that there are 44.01 grams. Most of you just probably know that off the top of your head, of carbon dioxide per mole. Again, this is scratch work. So I actually have 0.57 moles of CO2. So this is in my number of moles. So I've got one volume, one temperature. They're asking me for pressure, and I have got my number of moles. So I have everything I need to start this problem. So we write down PV equals nRT. This time I am solving for pressure, so I need to isolate that variable. Basic algebra, we're going to divide both sides by volume. And I get pressure equals nRT over V. N is the number of moles. We just found that right here, so that's going to be 0.57 moles. R is the universal gas constant. I'm going to look that up in my packet. Now keep in mind that they didn't give me pressure in this problem, but they did specifically ask for that pressure in atmospheres. So I'm going to look at these choices. This first one is the one that has atmospheres in it, so I'm going to use 0.0821 liters, atmospheres, moles, Kelvin. The temperature in this case is 200 K. I did not have to do anything to it because they gave it to me in Kelvin. That was really nice. That whole thing is divided by the volume that they gave me in the problem, which happens to be 4 liters. So let's make sure that everything cancels. Moles are canceling there. Liters are canceling. Kelvins are canceling. And the only unit that I am left with is atmospheres, which I know is a measurement for pressure. That's exactly what I'm looking for. So now it's time just to put everything in the calculator. You're going to multiply everything on the top together, hit equals, divide that by 4, and you should be getting 2.34 atmospheres. And we're actually going to label that CO2 because we knew what this one was, and that's just good chemistry practice. Now, again, this might be a little bit of overkill, but you might want to make a note that this number came from the reference table packet. And again, we selected that unit based on atmospheres because that's what I was asked to solve for. So you can see these problems are just really straightforward, very easy. We're going to do one more. I don't think most of you need it, but just to be on the safe side, we're going to go a little extra here. So here's our last problem. Again, I would encourage you to jot this down, and then we'll go over it together. So number 3 says, at what temperature in Kelvin will 3 moles of a gas exert 1.5 atmospheres of pressure inside of an 8,000 milliliter container? So let's highlight what they are asking me for. That would be temperature in Kelvin. Let's label what we have. I have the number of moles. That's nice. I didn't have to convert anything. 1.5 atmospheres is the pressure. 8,000 milliliters. Now, I cannot plug milliliters into the problem, but I do know that 8,000 milliliters is the same thing as 8 liters. So I don't really think you need to see that math. You just divide by 1,000 to do that metric conversion. So now everything's ready to go and ready to plug in. Remember, I had to have that in liters because when I plug that universal gas constant in, it's liters, units, some unit of pressure, mole Kelvin. So because it's got liters as part of the units, that's why I have to have liters there. Then everything, we're comparing apples to apples. So let's plug in. Let's write down first. PV equals nRT. This time I am solving for the temperature. To get temperature by itself, basic algebra, divide both sides by nR. We're just isolating temperature. I like to flip it around. Temperature equals PV over nR. So temperature equals pressure, which was 1.5 atmospheres, times the volume, which we just found was 8 liters. N is the number of moles. They gave that to me. That's 3 moles. And the R value is going to have to be based on atmospheres because that's the unit of pressure that I'm using in the problem. So once again, I'm going to use 0.0821. Liters, atmospheres, moles, Kelvin. Let's make sure everything cancels. Atmospheres cancel, moles cancel, liters cancel. That leaves me with Kelvin. Once again, that is great news because I am indeed solving for temperature in this problem. So I'm going to multiply 1.5 times 8. I'll just go and do a little intermediate step for you this time. That is 12. Then I'm going to multiply 3 times 0.0821. That is going to be 0.2463. Again, just a little intermediate step, scratch work. Once you divide, you will get the final answer, which is 48.72 Kelvin. Now, because they asked me for the temperature in Kelvin, I'm good. This problem is done. I will tell you, what if they would have asked for this temperature in Celsius? What would you have done? you would simply convert from Kelvin to Celsius by subtracting 273. So that's a really easy switch. I see that in a lot of problems, so just look out for that. Sometimes they'll kind of sneak that in there, but what they want you to know is when you plug temperature into that problem, it always has to be in Kelvin because that is what your universal gas constant is also based on. So that's how we use the ideal gas law, PV equals nRT. Again, your clue that you're using this law and not one of the basic gas laws is that you're only going to have one pressure, one volume, and one temperature. One of them you may be solving for, but it's just one of each. And you will also have the number of moles. If you'll remember with basic gas laws, there are no moles involved. Also, when you do these, make sure if you don't have it memorized that you have your reference table packet in front of you so that you can quickly look up the universal gas constant.